Now I have a slide for the person on it. So if everybody can wait just a minute while we prep to go live. All right, so I'm going to have to turn down the sound while we prep to go live. All right, so we are live. Welcome everybody to the April meeting of the Grand Strand Astronomers. We're here at Coastal Carolina University, as we always are. Of course, we also have some people on the Zoom link. So we have people both in person and virtual. So we're really excited tonight. We have a very good presentation by one of our resident astrophysicists, Dr. Dominic Ludovici, who is an expert in radio astronomy, amongst other things. But in addition to being a professional astrophysicist, he also has a lot of experience with telescopes and observing. So he's kind of got both a foot in both worlds. So what I'm going to do is I'm actually going to let him introduce himself, and I'm going to bring up the presentation and turn it over to Dominic, because that's I'm sure nobody wants to hear me talk anymore. And let me just share the screen. So I know I have a mic if you want it, but I don't think you'll need it.
Okay.
All right, so I'm going to turn you over and to controlling the process.
Hello. Thank you, Ian. My name is Dominic Ludovici, and I am a professor here at Coastal Carolina University. And I'm going to be talking to you all today about radio astronomy, in particular, what we see in the universe with radio light. So, first of all, what are radio waves? Well, you'll actually hear me kind of interchangeably use two terms here, radio waves and radio light. And that's because radio waves, like we're used to with listening to the radio in our car, or using our cell phones or wireless communications, they are just another type of light, just like visible light. Except for radio waves are very low frequency and low energy compared to visible light. One nice thing about radio waves, though, is unlike ultraviolet or X-rays or infrared light, radio waves can actually make it to the surface of Earth. So the optical telescopes and the radio telescopes are the ones that we can actually put firmly on the ground and use without having to worry about the atmosphere not letting any of the light through. But radio telescopes also look familiar, even if at first glance they seem quite different. The normal kind of Cassegrain type telescope we see on the left here, the light comes in the front, reflects off the curved mirror in the back that causes the light to converge. It reflects off a secondary mirror, continues converging, and then goes out the back of the telescope to either a camera or an eyepiece. A radio telescope actually works optically the same way. Light comes in from the stars. That light is reflected off of a parabolic dish. It reflects up and begins converging. It then hits a secondary subreflector, and it continues to converge until it enters a feed horn or a receiver down in the back of the primary dish. So optically, the radio telescope and the optical telescopes you may be used to seeing work exactly the same. But some radio telescopes actually look really different as well. This is an image of the long wavelength array down near Socorro, New Mexico. You can see in the upper right of the larger photo there that there's some of the more traditional style antennas from the Very Large Array in the background. But this long wavelength array is actually just a bunch of dipole antennas hung up in these kind of pyramid shapes spread throughout a field. And this radio telescope can also image and detect the radio waves from space, even though they look quite a bit different. So let's take a few minutes and talk about radio power and radio waves, and a little bit about why they might be hard to detect. Man-made emitters are sometimes quite powerful, sometimes not. A typical cell phone emits at about 0.6 watts if you're near a receiver and have good reception, or 3 watts if you're having troubles getting good reception. And radio waves might be broadcasting at kilowatts of power, but the black hole at the center of our galaxy, Sagittarius A star, actually emits 10 to the 32, or 10 with 32 zeros after it, watts. That is a huge amount of power. So you would think, oh, okay, great. Radio sources are probably pretty bright in the night sky. But there's another problem with that. The intensity or how much power it puts out is not how much energy you receive. So the flux or the brightness of a source is what you would actually observe. And the brightness depends not only on the power emitted, but on the distance to the object squared. So even a cell phone at 1 kilometer away, it's a pretty decent distance away, but that 3 watts at 20 kilometers is a lot brighter, actually 1,000 times brighter than the black hole at the center of our galaxy, just because the black hole is so far away. So we've got really weak radio sources, and we want to be able to detect them. So let's talk a little bit about the history and the birth of radio astronomy, and then we'll get to look at some of the cool telescopes that radio astronomers use. Radio astronomy was really born in 1933 by Carl Jansky and his discovery of extraterrestrial radio waves. Now, the interesting thing is Carl Jansky did not fancy himself an astronomer. He had no intention of doing any astronomy when he set out. He was a radio engineer for Bell Labs, and he was given the task of determining how the interference that was plaguing the telegraph, telephone wires, and radio communications, where it was coming from. So there was a lot of interference that they couldn't explain, and they wanted to get rid of it. So his job was to figure out where it was coming from. So he built this antenna that you can see in the large photo there. It had a bunch of dipole, just wire antennas across the top, and you could rotate the whole thing around in a circle. And this Jansky antenna was enough that he was able to detect the source, start getting directions for it, and he noticed that it came back once every 23 hours in 56 minutes, which is the sidereal rotation period of the Earth. It's how long it takes for a star to go all the way around the sky and come back. It wasn't following the sun, so it wasn't probably on a man-made timer. It was following the stars. He made this discovery, he published about it, and then the work was kind of forgotten for a few years, probably because the world was in the middle of the Great Depression at the time. Until in 1937 came Grote Reber. Grote Reber is kind of the father of modern radio astronomy and the father of the radio telescope. Grote Reber was a radio engineer from Chicago, and he got very interested in Jansky's work and Jansky's findings. And with the knowledge that he had gotten from Jansky, he decided that he wanted to map the radio sky, not just determine that there were radio waves from the sky, but actually map the structure. And this guy set out to build his own radio telescope in the backyard of his house in Chicago, which he completed in 1937. This telescope is actually really fascinating. It's still around. The telescope now resides in Green Bank, West Virginia at the Green Bank Observatory. But he scrounged a bunch of parts from junkyards and scrapyards to put this together. The main axle that spins the telescope is out of a Model A Ford. So he just took whatever he could get and he built this telescope in his backyard. And with it and a strip chart recorder and more patience than I think I have nowadays, he went through and made by hand radio maps of the night sky. And was the first to really do that and the first to build one of these proper reflector type radio telescopes. A few years later, after World War II had ended, the US government decided that it needed to get involved in radio astronomy and also ensure its continued success. Radio broadcasts were really taking off. TV was starting. Radio was popular, and radar for planes, etc., were going on. And we were even starting to get into the space race. So in 1958, Congress founded the National Radio Quiet Zone. This is an area of 1,300 square miles in West Virginia and Virginia that is a preserve for radio astronomy. Anyone that builds a radio transmitter within that region has to get approval for the transmitter from the observatory. So most of the transmitters in this region are actually directional. They don't broadcast in all directions. They only broadcast away from the observatory. And so it gives you some interesting times with your cell phone where it's working really well and you drive past the tower and it stops working completely. And because radio sources are so faint, there's actually a lot of very interesting rules, especially as you start getting closer and closer to the observatory. For instance, when you're actually at the observatory, you're not allowed to drive a gasoline-powered car because the spark plugs in the engine sparking cause enough radio interference that the telescope can't see what it's looking at. There's no microwave ovens on site. Your cell phone doesn't work. Your car radio doesn't work. There's no Wi-Fi. One of my friends that was living down there took their iPad with them and they had to get an adapter to plug an Ethernet hardwire cable into their iPad to make it work. Even your digital camera isn't allowed to be taken down by the telescopes. It's one of the few places I know that still sells a large amount of photographic film because the digital cameras will cause a lot of interference with the telescope. So it's really a fun region. And up until a few years ago, they even continued using these old 1971 diesel Chevy Suburbans because they didn't have computers in them. But after 50 years, they were getting a little worn out and they finally had to replace them. But it's a really fascinating place to visit. So what are we protecting at the National Radio Quiet Zone and for the observatory in Green Bank? Well, the National Radio Astronomy Observatory was founded along with the Radio Quiet Zone, and it was originally located in Green Bank, West Virginia. And at the Green Bank site, they began constructing telescopes. The telescope on the far right there is the 140 foot. That was the one that was construction began on first or second, I think second at the site. And it's an amazing piece of engineering. It's the world's largest equatorially mounted telescope because they didn't have the computers to track the stars on 2 axes at the time. So they equatorially mounted it, and there's a single 17-foot in diameter steel ball bearing that is the that holds that whole telescope up. It's on oil pads. It kind of levitates on a thin sheet of oil. And 3 separate manufacturing companies went bankrupt because they cooled the ball bearing down too fast and it shattered from thermal shock. And the only reason why it was 17 foot in diameter and not 20 was because the train tunnel to get to Green Bank was only 17 foot across. So it's a fun instrument. But it was taking a really long time. It was a huge undertaking, especially after they broke the primary piece of it 3 times. It was way behind schedule. So to be able to start cranking science out and continue getting funding, they built the 300-foot radio telescope, which is that center image there. The 300-foot telescope was built on the cheap using basically bridge parts. So they put it together more like an erector set instead of having everything custom made. Now, this telescope was a transit telescope. It couldn't move east or west. It could only move north and south and relied on the Earth's rotation to point it at things. And that telescope had a design lifetime of 10 years. It wasn't supposed to last very long, but it continued to operate for almost 30 years until a sad day in 1988 when it pancaked in the middle of an observation. I actually have got to talk to the telescope operator that was running the telescope at the time. He set it up to do a scan. He went to use the restroom, sat down on the toilet, and the telescope came in through the roof while he was on the toilet. Talk about scaring the crap out of yourself, right? So he was okay, little banged up, but okay. But the observatory had lost one of their crown jewels. So, but they were lucky. Senator from West Virginia, Robert C. Byrd, managed to get money through Congress to build a new telescope. And the result of that effort was the Green Bank telescope. The Green Bank telescope is 110 meters in diameter. It's larger than a football field. And it is a fully steerable telescope. It can rotate as well as point up and down. And it is the largest moving structure on land. It is bigger than anything else on land, at least, that can move. These pictures don't really do it justice in showing how big it is until you look in that top right picture and you notice those small white rectangles in the bottom right corner are semi-trailers. So this is really an enormous object, and it has done an amazing amount of research now over the years. But as big as these telescopes are, you're probably thinking, well, that's so much bigger than any optical telescope we have. It must be amazing. But there's a problem. It collects a lot of radio waves. It's very sensitive. But if you look at how optics work, there is a limitation on the resolution of a telescope, and it depends on the wavelength of the light you're looking at and the diameter of the telescope. So 100 meters across is a pretty big diameter, but it fails in comparison to the really long wavelengths we have when studying radio light. So you either need to go to high frequencies or have big telescopes. To put this in comparison, an 8-inch optical telescope the diffraction limit for that, the resolution limit for that 8-inch optical telescope is equivalent to an 84-kilometer in diameter radio dish. And I don't know about you, but going from 100 meters to 84,000 meters is a big jump. So what can we do? We have a trick up our sleeves as radio astronomers, and that is interferometers. This is an image of the Very Large Array. It's a telescope I mentioned earlier down in New Mexico, also run by the National Radio Astronomy Observatory. And the Very Large Array is a combination of 27 radio antennas, and they can actually be moved by rail through the desert. And we can station these telescopes up to 36 kilometers apart from each other. And what this does is, if you look at the interference between the signals of a pair of telescopes, that interference actually depends on the structure of the radio light coming from the sky. And you can use the computers to synthesize a telescope that is the size of the largest separation between two antennas. So with a Very Large Array, we can make a 36-kilometer across telescope out of the many smaller telescopes. But even this doesn't get us to our 8-inch optical telescope. But there is a way we can beat it. Instead of just 36 kilometers across the desert in New Mexico, what if we put a telescope in Hawaii and a telescope in Washington State, in Arizona, New Mexico, the Virgin Islands, and New Hampshire? Well, this is what we did for the Very Long Baseline Array. These telescopes, the maximum spacing is 8,000 kilometers apart. That gives this instrument resolution that surpasses any other telescope we have. It's got better resolution than Hubble, better resolution than any optical telescope we've ever built, by far. If you are big into astronomy, you may know we use degrees, arc minutes, and arc seconds to describe size scales on the sky. Typically, the atmosphere blurs a star to a few arc seconds when making optical observations from the ground. So if you've seen a star through an optical telescope, they're usually a few arc seconds in scale across. This telescope can accurately detect positions down to half of a micro arc second, or half a millionth of an arc second. But radio astronomy is also not just for the pros. There is a thriving amateur radio astronomy community. Some of these telescopes are repurposed satellite dishes that they have got a new receiver for to make it work for making observations instead of just picking up TV. Software-defined radio is helping with that a lot as well. Others are purpose-built antennas that are specifically designed for radio astronomy, for either amateurs or for student projects. And there's a lot of organizations that get involved with this too. For instance, there's the Radio Jove project from NASA. You can see on the right a small Radio Jove receiver and the dipole antennas that it connects to below it. And those can be used to observe solar storms and magnetic storms on Jupiter. Basically the equivalent of the northern lights on Jupiter. You can hear it in the radio from Earth. And there's the Society of Amateur Radio Astronomers as well. And NRAO even has a amateur astronomy site. It's a little old at this point, but it does still have some good links. Also, if you're interested, I have links to all of this at the end of my presentation with QR codes so that you can just take a picture with your phone and go to the website for all of these places. So we've talked a little bit about telescopes and how we observe in radio astronomy, but what can we observe? Why is radio astronomy better than optical? Or at least, how is it different? Well, one of the big things is in the spectral lines and what we can observe. Hydrogen gas, just regular old hydrogen, doesn't emit optical light. It's completely invisible in the optical. But there is what's called the 21 centimeter spin flip transition that is emitted by hydrogen gas. And when this transition occurs, you get a 1.4 gigahertz or a 21 centimeter radio wave. And this allows us to trace the gas in galaxies that otherwise would have been invisible. And also has provided us our first evidence for dark matter. If you look in the bottom right, there's a pair of images. The left image is optical light. I've inverted the image just so it's a little easier to see the structures around that galaxy. But in addition to that, on the right is the exact same image with the exact same scale using the 21 centimeter radio observations of hydrogen. You can see that the galaxies in the optical image seem more compact and well separated from each other. But in the radio image, you can see these long tails of gas that are being strung off of that central galaxy, reaching out and touching the secondary galaxies around it. And what we're seeing here is actually the beginnings of a merger of multiple galaxies colliding with each other. And they're beginning to gravitationally interact. An image on the right here at the bottom is actually an image from my senior thesis when I was an undergraduate student. This is a galaxy that I discovered back in my undergraduate days. We took radio observations, and that 21 centimeter radio observation is shown in the contours in that image. Whereas the black and white is again another optical light image. And you can see in the very center of that set of contours, there is a faint smudge. That faint smudge is a galaxy with stars just like our own. But this galaxy is, let's say, I'm not going to say young, it's probably old, but it hasn't seen a lot of interesting things happen. Not many stars have formed from it. Most of the gas is just kind of sat there instead of collapsing into stars. So you can see that there aren't very many stars in it, but if you look at the radio contours, you can see that this galaxy is much larger and much bigger when looking at the radio light than you would ever have guessed from the optical. In fact, it's so faint in the optical that no one even noticed it was there until we put the radio contours over top of it. In graduate school, I worked on studies of the center of our galaxy, the galactic center. On the left, you can see a beautiful image of the galactic center area in optical light. You can see some stars, some nebulae, and all of these dark areas where it looks like there's nothing. But those dark areas aren't there because there's no light being emitted. They're there because there's so much gas and dust in the interstellar medium that it's blocking all the light from behind it. And because of all that material, we can't actually see the center of our galaxy from here on Earth in optical light. It's impossible. So what can we do? Well, radio waves travel through all that gas and dust with no problem at all. The image on the right is a radio image of the galactic center. And you can see here that there's all kinds of interesting phenomenon that you can't see in the optical. There's supernova remnants. There's molecular clouds, massive star clusters. There's the black hole at the center of our galaxy. And there's even some of these long, thin threads in filaments that trace the magnetic field in the center of our galaxy. And you can't see any of that in the optical. Now, in the infrared, you can actually see the center of our galaxy. The infrared light can make it through as well. But even with the infrared light, you miss a lot of things that you can't see in infrared that are visible in the radio. And in the radio, you miss some things from the infrared light. So this is part of the, this is the sickle and pistil regions in the galactic center. And the top bit is a nebula. That's what we call the sickle. And then the round part in the bottom is the pistil nebula. It's an old dying star. And you can see in the infrared, there's a huge star cluster there. There's all these bright pinpricks of light from these young stars. But you completely miss those in the radio on the right. But on the right, you get these long, thin filaments that are tracing the magnetic field in the center of our galaxy. And the bright white point in the middle of that filament towards the bottom left of the radio image is a supermassive black hole in a galaxy beyond our own that's shining through our entire galaxy to get to us on here at Earth. And you can't see that at all in the infrared. Another fun thing that's kind of extreme that radio waves can let us look at is radio pulsars. These are neutron stars, basically failed black holes. And they are formed in a supernova explosion if the star is not quite big enough to make a black hole. These neutron stars have a mass of about the same as our own sun, but they're only about the size of Conway. So they're really massive, but really compact. And they can rotate as fast as your kitchen blender. So they're really extreme objects. As they rotate, they generate beams of radio waves that, when they sweep past Earth, blink like a lighthouse beam would blink. And we can use these to test Einstein's relativity. So far, it's passed every test with flying colors. And they're even starting to use arrays of these that they're monitoring to try to detect gravitational waves. What's really fun about these is, since they're so massive and they're spinning so fast, they are incredibly accurate timekeepers. Some of these pulsars are so accurate in keeping time that they are better clocks than our own atomic clocks. You could actually calibrate our atomic clocks off of these instead of the other way around. There's also things like radio galaxies, where we get these huge lobes firing out of a center optical galaxy that looks much more unassuming in optical than we would ever get in radio. In this image, the radio is the red and the white is the optical light. And so much more. We can study asteroids. We can use planetary radar to detect new asteroids, map the surfaces of the moon and Venus. We can use molecular lines to detect things like methanol and ethanol, ammonia, and so many more molecules in space, including some basic amino acids. The sun is a large radio source. It's the brightest radio source in our sky. And we can study the solar storms and magnetic storms on the sun. Jupiter has its own magnetic storms. And the cosmic microwave background, the light that is left over from the cooling of our gas of the universe in its early days is now observable in the radio as well. And although they've not been found, there have been many attempts to look for extraterrestrial life with radio telescopes as well, because if they're advanced and they're broadcasting radio waves, we should be able to pick them up with a radio telescope. But the future isn't all bright for radio astronomy. The radio skies are dark no longer. There's radio frequency interference caused by just about anything, it seems. Cell phones, radios, microwaves, and even things you wouldn't really think about, such as spark plugs, even electric motors, computers, etc. There's an observatory down in Australia that they thought they had made a very exciting discovery of these really bright, really fast radio bursts, until they realized they were all coming in between the hours of 12 and 1, and that's when the microwave was being used. And if someone opened the microwave door before it finished running, you got a short pulse of radio waves at the telescope. We talked a little bit about cell phones and how they're so bright even a kilometer away. But if I took my cell phone, put it on a rocket and launched it and landed it in a crater on the moon, it would still be the third brightest source in the radio sky, only rivaled by the sun and that black hole at the center of our galaxy. So just as a little experiment, I brought a small radio with me. I have it set to AM. Hopefully this doesn't annoy any of you too much, but I wanted to show you just even the sources of radio interference that we can pick up with an AM radio in this room. If we turn it on, I don't have it tuned, it's just static. But if we walk over to here, it's a little quieter. Go up to the projector. The computer over here does the same thing. So even with a little old Walkman radio, you can detect a lot of interference. Oh, I'm sure you understand. I have a recording here as well, but it is super annoying to listen to. It's a recording of the radio noise from my old Ford Ranger pickup truck. That if you tune to the AM radio and started driving down the road, you could actually hear it rev. You could hear the spark plugs. So let's give it a try. Hopefully it's not too loud here. Maybe.
Oh, it's going to be, it's turned off because we're getting it from YouTube.
Oh, okay. Never mind then. But you can hear it go as you rev and it shifts. The windshield wipers on that made an atrocious amount of radio noise. My newer car is better than the old Ranger, but still not immune to these things. All right, so that kind of wraps up my talk. As promised, here are QR codes to 3 amateur radio astronomy resources. The Society of Amateur Radio Astronomers, or SARA, the National Radio Astronomy Observatory, so you can learn more about radio astronomy and the telescopes we use to study the universe, and then a link to the NASA Radio Jove site, where you can get your own Radio Jove telescope for about $200 if you want.
I think a picture of all 3, or I have to do each one individually.
I think you can take a picture of all 3, and then your phone can let you pick which one you
My
want.
phone's smarter than me.
It's smarter than me too. So.
And Radio Joe, if you've got an amateur radio receiver, you've actually got a lot of the pieces to do it.
Yeah.
Because frequency is, I think, around 21 megahertz.
Something like that. It's
for Jupiter emissions.
It is low frequency. So
you just need a sufficient dipole.
yeah.
Okay, I have just, again, I'm new to all this. I
Yeah.
have general knowledge of just everything, sort of pretty much. When you're looking at the night sky, light, you write, write a section, declaration, that.
Yep.
But if I'm a school teacher, and if I wanted to study the sun in radio frequency with my kids, versus someone else in the room wants to study and find a pulsar, are we looking for a specific frequency for the sun versus how do we know that we're looking at the sun?
So
Radio waves, and how do we know we're looking at the pulsars?
it depends on what you're looking for. So for the sun is broadband. It emits frequencies, basically every frequency. Some are stronger than others, but it emits over all these frequencies. So mostly for the sun, it's point a telescope at it and you will get the signal. For things like radio pulsars, they went undiscovered for a long time because those blips are happening every, like even for the slow ones, you get one blip a second maybe, but that blip only lasts a millisecond at most. So they went completely unobserved for a long time just because if you average the signal out, you can't see them because it's like flash on for a second, off.
Can't you look at the pitch? Usually, I think I watched some video where you can determine the different pulsar by its pitch.
You
like
can,
the one in the Crab Nebula. Versus,
so yeah, so they all have different spin frequencies, so
Right.
they turn on and off at different speeds.
So that
So-
radio telescope can't pick the
Well,
pitch up.
if you can, but to be honest, pulsars require very expensive receiver equipment to see because you have to be able to collect your radio wave, process it, and save it every 100 nanoseconds or something like that.
So you really can't be an amateur person.
Yeah.
Great, a
This
pulsar
is-
research. You have to be a green bank or something like that.
Right.
So-
And pulsars are actually fairly faint. So even a telescope like the 40-foot telescope down in Green Bank, you can detect maybe 1 or 2 pulsars with it, but even with that big of a dish, they're difficult.
Jocelyn Bellin, she didn't do her work at Green Bank. She did it over.
Cambridge over in the United Kingdom.
Okay.
Yeah. And she had an antenna that spanned like an entire farm field.
So
to do her
somebody
work.
said to me, I want to do pulsars really in the classroom. It's sort of tough, but you can do the sun.
Yeah.
You have a radio telescope. in the
Now-
classroom.
I don't know if it's still running, but when I actually got my start in astronomy research by being that pesky high schooler that went down to the physics department and said, I want to do research. And I started working with a professor called Maura McLaughlin at West Virginia University. And by the time I had left, I had apparently inspired her to start a program called the Pulsar Search Collaboratory, which was sending radio pulsar data from the Green Bank telescope out to high school students and having high schoolers process the data and discover their own pulsars. And the students even got to like go present their work at a conference and things like that. I don't know if that is still running.
I've seen it. I know
Yeah.
there's a whole professional development teachers had to do in order to,
Right.
use it and all that. And it's all the data, the archive data. you're
Right,
looking at.
that's a different program he's talking about.
Okay.
There's a NASA program that lets you use real data in your classroom, and you have to go to training.
Yeah.
Now, if you have a student who's particularly interested, there's also a summer program that runs for like a week or a week and a half. in
Mhm.
Green Bay.
Yeah,
Yeah.
I've already told my kids about it.
Run,
They were
run
advertising for it.
Yeah.
led by Dan Reichart at UNC in Chapel Hill.
Mhm.
He takes a group of students up
Mhm.
and they don't get much sleep. And they basically work on a project.
Yep.
For like I think the week or week and a half they're there. And they learn a lot about radio astronomy. You get to use I think you do the 40 foot dish.
Yep, the 40-foot's their educational.
Because I do know
telescope.
of a teacher who had one outside their classroom, a radio telescope, like a dish like you were showing.
Yeah.
So I guess, so they were probably just doing sun data then, that's something really easy for
So-
a classroom to do.
Small, so a telescope like your standard direct TV dish,
Right.
that's going to mostly be good for the sun and maybe Jupiter. A like 1, 2, 3 meter dish, like a 10, 15 foot old style satellite dish, you can actually start to see the neutral hydrogen from our galaxy, and you can start by looking at the frequency that you get that wave in at and comparing it to where it should be. You can actually map the velocities of all the gas in the galaxy and make what we call a rotation curve, which shows you how different parts of the galaxy, how fast they're moving in their orbit around the center of the galaxy.
So it's sort of like light, the bigger the dish, the
Right,
better the
yeah,
astronomy.
just like any
light
telescope.
right?
Yeah. So the
So Great
so-
Bank is like every astrophysicist wants to probably go to Great Bank and get time on the telescope.
there's a lot. Honestly, the very large array down in New Mexico is the super oversubscribed one, but Green Bank is very popular as well. Unfortunately, like the direct TV dish is like me trying to do astronomy with my cell phone camera. It'll see some stars, but it's not an ideal instrument. So the 40-foot radio telescope is getting into more of like your 8-inch kind of class, and then going up to the Green Bank telescope is like your 10-meter. Yeah, so but some of these telescopes, you can do some interesting observations even with fairly humble equipment. Doing the neutral hydrogen, you might want to turn and like get a kit that has a nice receiver that you can change what frequency you're observing at by, you know, hundreds of megahertz at a time, or not megahertz, hundreds of hertz in an interval to kind of, because you go to this frequency, make a measurement, go to the next, make a measurement. So you need to observe the whole spectrum. Well, not the entire spectrum, but over the course of several megahertz, you have to make fine measurements to do that kind of work. It's something an amateur can
ISTAR
do.
computers, can they be used, those small ISTARs?
I'm not familiar with those, so
Little nano computers.
A lot of people are using SDR now. There's a lot of amateur radio astronomers
Yeah.
that are
I can't
using
afford that.
little software-defined radios
yeah,
that,
That's expensive.
and you know, but and they work very well on the receiver side. The trick is when you're actually building the feed horn, and that's the really tricky bit.
Yeah.
To make sure that you're not getting interference, and that's the part that takes actually some pretty good
Yeah.
engineering.
The amplifiers, you have to get
Right.
low noise amplifiers too.
There is
Those
a
are
company, there's
usually,
an amateur radio astronomy company now
Mhm.
that sells, what is it? Something low. That sells like
Yeah.
low noise amplifiers now for amateur radio astronomy, like $100 or something.
Yeah.
I think. You know, yeah,
There-
that's the tricky bit, right? The
Yeah.
back end receiver part is getting really easy with the software defined receivers.
Yeah.
You can actually tune those pretty precisely.
Yeah.
I follow several groups that do a lot of this, but you know, it's the actual scope is actually still a little tricky.
and one other little thing that maybe kind of impress a little bit as to how faint terrestrial or extraterrestrial radio waves are, is if you collected all the radio waves from every radio telescope that has ever existed, all the radio waves we've collected has less energy than a single falling snowflake. So they're pretty faint, which is why we need such large dishes. Also, something like your old direct TV dish, the beam, the pixel on it is several times larger than the full moon on the sky. Makes it easy to point, you just kind of have to get it close, but you're not going to be getting like really detailed maps of things, because even going to like the 40-foot telescope, you're still talking like a degree across like 2 full moons on the night sky.
Can't build those direct TV dishes. A lot of people have.
I've seen a few down at the, what's called Habitat for Humanity.
Yeah, I mean, you can build a simple radio telescope with that, but literally you look at the moon, sun, and you can point it. Sometimes you can get such a signal off a big tree or a person, but I mean, that's about it, right?
The guy that I know that has Hannibals, it's not this big. It was bigger than the direct TV dish.
Yeah, it was like one of the old fashioned like 80s, 90s satellite dishes.
Yeah, I think somebody donated, I think the Astronomy Club donated it to him, but it was a larger dish, probably 3 or 4 feet across.
So
once you get in that meter class, you can start doing some interesting things.
Yeah.
And I mean, it'd be neat because we'd be collecting data, like that's the part about radio astronomy, you go 24/7, so.
Right.
And it would be neat to have for kids to even see if we have a storm or something, to change in the radio frequency or something from.
Yeah, you can pick up lightning really well. Lightning's really bright in the radio. If you've ever been driving down the road with a radio that doesn't quite have the arresters, the good arresters in it, in the lightning storm, you hear when the lightning flashes. But there are kits you can buy. I don't know if the MIT Haystack kits are still available. I didn't hear great things about them anyway, but they were pretty expensive. They were thousands of dollars.
I mean, if you spend that kind of money, there's a company out of Italy called Prima Luce that sells radio telescopes all set up and good to go.
Yeah.
But I mean, you're going to spend 15, 18,000, but you get a good one that's able to track. It's full motion,
right?
And it's well designed.
Yeah.
And they're the bigger size, like that he's talking about.
Yeah.
And there's a couple of somewhere in South America, there was a school that actually got together as a project and built one. And that information's online, but again, it took them like a year to build it.
Yeah. So,
so it's
Yeah, that Einstein, man, he's hard to prove he was wrong. That man was amazing.
yeah.
So everything gives off radio waves, everything, right? Pretty much.
Most, I would say actually yes. So you know how when you are cooking with like an electric stove, when the burners get hot, they get that dull, deep red, and then they get redder and then orange. And if you're being ambitious and maybe pushing things too far, crank it up real high, they start to get yellowish. That's because they glow because they're hot. It's called black body radiation. But if you go down to human temperatures, you're in the middle of about the infrared. That's how those heat cameras work, is the infrared light. If you go down to like things that are 3 to 10 degrees Kelvin, so just above absolute zero, their black body radiation peaks in the radio. So you get the thermal emission from the radio. Now, all of us are still emitting radio waves because we have a temperature. Because although the peak moves to bluer and bluer to higher wavelengths, you still have some of the low wavelength light being emitted. But me emitting light because I am warm it's a very small amount compared to most other things. Though with a very sensitive radio telescope like the Greenback telescope, they actually have to cool their receivers with liquid helium to bring them down to like 0.5 degree Kelvin, just above absolute zero, to keep them from generating noise just because they're warm.
I'll also say, sorry, but
Yeah.
for anybody that's interested, Green Bank does tours.
Oh yeah.
They have a regular tour, but they also sell tickets for a tour where you can go back in the design shop and see how they design the feed horns and everything.
I missed it when I was living in Pittsburgh.
And you can see how they design it, and they take you back in the labs and do that. It's a good tour. I would advise anybody that's really interested in it to take that tour. The only thing is you have to buy the tickets in advance, because there actually is, they do have to do a security clearance and everything for you. But they are actually doing it again in May. I saw a thing, they're doing it in May, and they're selling tickets for it. It's well worth doing.
And there's also, if you wanted to be there when there was a little more going on, There is, it's called Greenbank Star Quest. There's a big star party at the observatory.
I know that
So-
they're looking for, it's due today, they're looking for K-12 educators because they want to expand their radio teaching in the classroom. So they're asking teachers to come out, I guess, for help develop, curriculum for kids. So I know they do a lot of that.
Okay.
So yeah, a lot of outreach stuff.
Oh, we've got, I don't know how to turn the sound on.
Yeah, we have questions.
Poor Thomas here has been waiting to talk to me and I don't know how to hear it.
Waving his,
How you doing, Ian?
What do you teach at?
Can you hear me?
I can hear you now.
Okay, I just wanted to make an observation when you was talking about the spark plugs and stuff.
Yes.
Me and my wife, we don't use cable for television. We got a digital antenna in our attic.
Yep.
So at nighttime, certain times of the day, we have a neighbor son comes in with his pickup. Our TV goes haywire because of the way his truck is.
Yep.
Most likely he don't have his spark plug wires or not that good and so forth. So it even messes up digital signals.
Yep. I know that my neighbors probably get mad at me when I break out my welder in the middle of the afternoon too. So, and like, it's less noticeable with the newer digital TVs, but I very clearly remember growing up when we had the analog TVs still. My mom would get the blender out, turn the blender on, and all the TVs went out in the whole house.
Yeah,
Just noise.
yeah.
So there's, and in Greenbank, the radio quiet zone, they can enforce that radio quiet. Technically they can, I think technically they can arrest you for it, but they don't want to be the bad guys. But they were picking up really bad interference one day. And they got in their RFI truck. It's a truck with antennas all over it to track down this source of interference. And they tracked it down to a farm, like 10 miles down the road. And the farmer had put an electric blanket in the barn for his dog. And the electric blanket had a little short in it. And that's what was making it so they couldn't use the telescope. And they bought the guy a new electric blanket for his dog, and the new one was fine, and they let him go on his way.
Yeah, I've been
But
by
there
there
was-
many a times and my cell phone does not work in that area. You
Nope.
know, get to work.
I love it. I love being able to be like, oh, sorry, I'm not working right now. You can't get a hold of me. But
Most of them who live there are happy with it too.
yeah, so some people do love it. Some people find it as an annoyance. I also know they had Frontier for their internet company out there, and Frontier at one point sent wireless routers to everyone in the county. And then Greenbank made them come get all those routers back and go get ones without wireless in it because, even without that, like 2.4 gigahertz and 5 gigahertz where the Wi-Fi is basically ruined. You can't see in any of those Wi-Fi bands. But every time they announce a new frequency allocation to something that's at a higher and higher frequency, on one hand, I'm like, well, this is good for infrastructure and like transmitting data and all that. And the other part of me is like, my night sky, I can't see through that anymore.
Frequencies away from the ham radio operators.
What's that?
They're taking those frequencies away from the ham.
Are they?
Slowly but surely.
I didn't know what frequencies ham operated at.
There's a
So,
bunch of them, and they're slowly allocating them to
Yeah.
TV companies, microwave companies,
Yeah.
telephone companies.
yeah, well, first Wi-Fi was 2.4 gigahertz, then it's 5 gigahertz, and now they're talking about 8 gigahertz because you get higher data rates at higher frequencies. But that part of the spectrum was clear for us, and you could look at things really easily. And the 1.4 gigahertz right around the hydrogen line is protected for astronomy, but the rest of the spectrum is fair game. And when we lose it, we lose it. You can't get it back.
how's all these satellites Musk's putting up? How's that in the flying? Oh, sorry. You never asked the question.
They're frustrating for both optical and radio astronomy. So in optical, they fly through your long exposure and trail things, and it's frustrating. And in radio astronomy, there is now just a constant swarm of radio noise at those uplink, downlink frequencies. Well, it's already, damage is already done kind of at this point. I mean, it can get worse, but the first offender was the XM radio satellites. Those were horrible for us too. That was one of the first big offenders. And God help you if you want to observe the near geosynchronous satellite belt.
Don't they stay stationary?
They do, but the stars behind them move. So if you want to observe something that's even remotely near that band, it actually, you have to know ahead of time, and there's special calibration procedures you have to do on the telescope to keep it from just getting overloaded and destroying all your data.
My buddy just sent this. I don't know if this is old news or new news, but you're supposed to be 3 supernovas in the same galaxy. Has anybody heard that?
I haven't heard of that.
It's SN 2001, BN, EC, and PV.
You said SN 2001.
2001.
No, it has 3 supernovas in the same
What
galaxy.
was the supernova number?
The galaxy is NGC
What
56605.
was the supernova number you stated?
Yeah, the SN number.
SN 2022 BN,
Oh,
That's this
2022.
year.
That's this year.
EC, and PV.
Yep.
Sequence that number's about right for right now, so. Yeah,
Yeah.
that's possible.
It's possible. Highly unlikely, but possible. The universe is a big place.
Okay.
All
So,
right.
yeah, you can hang out for a few minutes. Yeah, so thanks to Dominic for a great
Thank you.
presentation.
Thank you.
Great presentation.
Just talk about a couple of things that we want to do, a couple of things that are relevant. This is kind of coming up. This is our April meeting. We, of course, will have one in May as well, but I kind of wanted to talk about outreach opportunities. There are 2 coming up. One is going to be at Brook Green Gardens on April 23rd. This is their Earth Day celebration that they're having at Brook Green Gardens, April 23rd, Saturday. It's from 10 to 2. So what we're going to do is, it's going to be very similar to last time, except we're going to be out in the more open field to do solar observing. You know, the big open field before. We are confirmed with that. I met with Stephanie Atkinson down there and talked to her about that. So we are going to have power, electric power, so we can run our telescopes and we can do solar observing from 10 to 2.
And we're gonna need a list of names for that, I guess.
We will need a list of names in advance so that you don't have to pay to get in. So you can get in for free. I think Denise is also ordering more solar system cards,
I've got
planet cards.
everything. I got a bunch of stuff.
Okay,
they sent
So we
out.
should have stuff to run,
Stickers, everything.
stickers, so we should have plenty of stuff to give away, and we'll do solar observing. Hopefully, if the sun is as interesting as it was for the last event, right, that we did at Brook Green Gardens, because the sun had some really good prominences and it was really active. So hopefully we get a break on the weather for that, right? So that's April 23rd, Saturday from 10 to 2. So anybody's welcome to come. The other thing, and one reason I asked Dominic to stay, is the other outreach thing that I think we should try to work on is there is a lunar eclipse in May. And I know Dominic was planning to try to get some people together to bring out the coastal telescopes and set up an area here. I think that'd be a good place for us to partner and bring some of our telescopes as well, right? So we'll have to get a suitable place, whether it's the lawn out here or near the parking lot somewhere. We'll have to work out the details. Did you remember the exact date on that?
It's mid-May.
Yeah, sometime it's mid-May.
I'll look up.
Now, the we'll try to get the university to advertise it because school will be out. So the students will not be here. But if we get some good advertising, we should get a fair number of the K through 12 schools are in session then. We should be able to get a fair number of those. It's actually really good timing for lunar eclipse because a lot of them are like 4 in the morning. This one actually you start seeing it about 9:30 at night, and it goes up till like midnight. So it's actually really good timing, right?
What
It's
day,
the 15th,
which is what day of the week?
Sunday.
So it's a Sunday night.
Less than ideal for those of you with kids going to school, but
Right. So, but the beauty is, again, you'll start seeing, again, it starts like 9 something, right?
Yeah.
So the good news is it's not too late. It's not like 4 o'clock in the morning, right? So that, I think it will be a great opportunity to do some outreach. Certainly, I certainly talk to Dominic all the time because we're both here. And, I think it makes sense to combine forces and get some good advertising and then just have a number of telescopes out. And then we just can bring it and we can service all the people from the public, right? So I think that makes the most sense, right? I know Astronomy Day is technically in May as well. There are some challenges with that because it's after school is out here. I think it'd be great to do an Astronomy Day event, but I think we're gonna have to do what some other places do and haul it in earlier next year. Right? Because you want to do it when things are in session on campus, right? So I think doing an Astronomy Day thing would be kind of cool, but I think we need to kind of talk about what that would look like, right? I'm afraid if we do it now.
State park or something, that's a lot of planning, I guess, ahead of time.
Well, it's a lot of planning and, plus a lot of people do daytime stuff as well as evening stuff on Astronomy Day, right? Which means you got to have people like putting together like some kind of exhibits or some kind of educational stuff. I would like to get there, right? Because I think it'd be really cool to do something like that. I know I talked to Dominic about doing stuff like that. But I think we could start this year. I would like to start with the lunar eclipse. And then I'd also like to use Coastal to help advertise for in December. I know that's still far away, but Mars will be, it's one of the 28-month cycles where it will be, it will be very bright and very easy to see in amateur telescopes. Usually those are kind of events get a lot of people out. And the beauty is it's not just one night. There's like 2 good weeks of observing. So you can pick, if you're going to have bad weather, you can pick a time. And usually that gets a lot of hype on like the news stations and the weather forecasters make a big deal out of how Mars looks big. And you end up getting a lot of people to come out. I think it's a good opportunity to organize some events around that, right? Yep. And December also generally is good weather here. So it's a good opportunity. So those are 2 really prime events. And of course, again, for those of you that weren't, before we came live, we're still doing our observing sessions at Hampton Plantation. We are still trying to arrange something with Play Card in Western Horry County. I think there's another one of the summer camps I think that they're going to try to arrange. Unfortunately, we've been weathered out every time we've tried, right? So when we do have the educational event at Play Card, anybody that is able to come, would be great if you could come, so that we can stay afterwards and do some observing and figure out if it's going to be a suitable site, another additional site for some dark sky observing, because I know that south of Georgetown is not ideal for people, especially living in the northern part of the Strand, right? For some of us that live in the southern part of the Strand, obviously Hampton Plantation is still a lot easier, but not everybody, it's not easy for everybody. The skies are very good down there. So of course, Hampton Plantation continues to work to be an IDA dark sky site. There's been a lot of activity on that, and things are moving along, right? So we're hoping to be one of the first, if not the first dark sky park in South Carolina. So they're actually working pretty hard. There's just a lot of things to go through. So that's really all I had. Does anybody have anything else they wanted to bring up?
I will be at Ocean Bay Elementary April the 19th. They're having their science night. If anybody's interested in bringing anything, it's like an Earth Day themed science night. So
Okay.
I'm probably going to focus on NASA citizen science and those kinds of things.
All right, so can you put out something maybe to the email list or something?
Absolutely.
Yeah.
But I will be there to cover that.
And
so.
what are you looking for?
It's just earth science based, so it could be anything. I mean, you could bring a telescope and have kids look at the telescope,
Is it
and,
inside?
you know, or you talk about light pollution. Yeah, I believe so. It's inside. I believe it's inside.
Are
Yes.
you able to make a poster of Jupiter at the school?
During
What we've done, what I've done in the past is we got the school to make a poster, one of Jupiter and one of the moon.
Okay, I'm going to stop the live stream,
And I
everybody.
have,
So,
I have a little telescope.
thanks everybody who came, who's listening to the live stream.
Okay.
And the other one had a telescope and they were to see the moon.
That's really cool, but I have a feeling that it's more of like a rotational